You and I have a rendezvous with destiny. We'll preserve for our children this, the last best hope of man on earth, or we'll sentence them to take the last step into 1,000 years of darkness. There's something going on in time and space and beyond time and space, which, whether we like it or not, spells duty.
Okay, folks, we're going to kick this off. Please welcome the Energy Panel, moderated by the one and only, extremely not boring, Packy McCormick.
All right. Do you feel the energy? Welcome to the Energy Panel. We have a great group here. We have founders, we have investors. We're focused on all sorts of nuclear. I know the fusion people don't like us to call it nuclear fusion, but we have nuclear fusion and nuclear fission represented. We have investors. This is going to be a lot of fun. To start us off, I'm going to go around the horn. Isaiah, let's start with you. Can you introduce yourself, what you're building quickly, and then we'll dive into the meat.
Yeah, so I'm Isaiah Taylor. I'm building nuclear reactors, and instead of making electricity with the nuclear reactors, we actually produce oil and gas. So we buy CO2, we buy water, and we create synthetic fuels using scaled manufactured nuclear reactors.
Great. I'm Tommy Hendrix, investor at Decisive. We invest in energy, defense, and infrastructure.
Morgan Hitzig, investor at Venrock, focused in a couple of key areas from an investment perspective. First on thriving cities, second on how do we actually get to the promise of Industry 4.0, and then how can an AI really focus us on taking ossified industries into the 21st century. Also still a Navy Reserve officer. Thanks.
Doug Bernauer, CEO of Radiant. We are working on the world's first mass-producible nuclear reactor, so 1 megawatt replacing a diesel generator. I was at SpaceX for 12 years before that. I'm an engineer and moved into nuclear to go solve that problem. And what we're doing is trying to not only mass-produce reactors, but for the first time in about 50 years in the United States, to actually fuel a new reactor design and get it tested, which is a massive hurdle.
I'm JC, founder and CEO of Fuse. So we're working on nuclear fusion for both energy and defense, commercializing technology that's coming out of Sandia National Lab, mostly for safeguarding our nuclear stockpile while also having a commercial path for fusion energy.
Awesome. So I want to start off with some myths around nuclear. There's safety, there's waste. If you're at Reindustrialize, hopefully you're over those myths. Nuclear is safe. It's more safe than coal for certain, and waste is really not an issue. I want to talk about some of the actual ones. JC, maybe starting with you. The joke is that fusion is always 30 years away and will always continue to be 30 years away. Why is that no longer true?
Yeah, so I think there's one critical event that happened last December where for the first time in history, the National Ignition Facility actually demonstrated that you could hit ignition burn. Now, it's still just a scientific demonstration, but we see it as the Kitty Hawk moment where this was demonstrated. So now it's a race to commercialize it and make it more energy efficient from an engineering perspective. And so we're working to develop the technology that makes it repetitive, that makes it cost effective, and leveraging decades and billions of dollars invested by the US government. And the second point, when people think about fusion, there's the energy perspective. But fusion has been mostly developed and after the Comprehensive Test Ban Treaty in 1996 when they banned underground testing. And so they built this above ground testing or fusion generators that actually support and are critical for our national security, supporting the nuclear stockpile mission, as well as critical space and ISR systems. So I think given the drive of momentum for national security that's pushing the urgency to develop this technology, as well as the NIF breakthrough, I think the timing is now to just continue it to make progress.
Awesome. And Doug and Isaiah, the knock on nuclear is solar is getting really cheap. Batteries are getting really good. They're coming down the cost curve. You look at nuclear, it gets more and more expensive. Why will that no longer be the case? Why can nuclear be cost competitive?
Yeah, so I think that nuclear always gets the wrong comparison here. The way that things get really, really cheap is by doing them over and over again, right? We get really good at and really low cost at doing something we do a lot. Actually, I think it was the former CEO of Westinghouse, which makes the AP1000, who said, like, look, if you wanted me to make cars and I was only making 1 or 2 cars a year, each of those cars would cost a ton of money, right? Like, there'd be $1 million Camry. So, like, that's kind of where we are with nuclear. And yeah, like, solar's getting super cheap. The reason it's getting super cheap is because we're making a ton of panels. But you're comparing nuclear, which I would honestly say is an infancy industry. Like, we really only build a few reactors a year as a civilization. When we're making hundreds of reactors, like, talk to me again, and hopefully we're doing that soon.
Yeah, that's well said. I love the mass production point. There are about 430 reactors in the world. We actually reached the peak of the build in 2016, unfortunately. There are fewer reactors today than there were operating in 2016. The other point is to make here is we're making a portable reactor, a portable mass-producible nuclear reactor. And if you do that, you can take it and put it anywhere in the world. There are a ton of locations in the world where you can't put wind or solar in because there's inclement weather. Think about the Arctic, right? Very, very far north or very far south on the Earth. These are really bad locations to try to go and put a project in where you have permafrost, where you have a very short construction window, right, in the summer. And typical solar installation might be 18 months best case, right?
Actually, I want to say one more thing about the waste. I think probably like everybody in this room generally is like pro-nuclear, but people actually still like really, really misunderstand nuclear waste. When I was raising money for this company the first time, I had an FAQ sheet, and I did the math on this. This is not a good way to dispose of nuclear waste, but it's an interesting thought experiment. So I did the math on nuclear waste. If you take a kilogram of nuclear waste that made energy, in a nuclear reactor, and you sold the energy, and then you have, let's say $100 from this, this amount of uranium, it's actually cost effective to put that on a Falcon 9 on an orbit to the sun. Like, it's about 6 or 7% of the revenue generated from that uranium is all it would cost to literally like put that into the sun. Now, we don't do that because there's like a lot better ways to deal with nuclear waste, but it's just not a problem. In fact, I think the U.S. Gov nuclear account on Twitter had like a super viral tweet a few days ago of 70 years worth of nuclear waste on this like tiny little field, right? And this is one of the biggest things that nuclear companies like always get questions about, like, what about the waste? What about the waste? And the funny thing is, they say like 70 years and we still haven't solved the nuclear waste problem. The reason we haven't like, quote, solved the nuclear waste problem and gotten Yucca Mountain open is because it ended up just not being a problem. Like you don't have to do anything with it. You put it in the cask and it stays there, and there's just so little of it, nothing really, it's just not a problem. So,
JC, what would you do if someone gave you a bunch of nuclear waste?
Yeah, so high energy neutrons that come out of fusion reaction or could be really useful. Now, you can use those to accelerate the rate of decay of nuclear waste and spent fuel, which means more energy, more heat. And that way you can use the nuclear waste as an energy multiplier. So just like 20 megawatt of fusion output can be 3 gigawatt theoretically of fusion power. And that's based on work that was done in early 2000s by Sandia and Los Alamos that actually published how using spent fuel could be an energy multiplication factor to make fusion a reality faster. Now, of course, there's caveats of if that's happening, then someone twitches, there's some proliferation concerns, but I think there's a viable path to being able to use high energy neutrons and spent fuel in a productive way to help get energy faster on the grid.
So I want to turn to some actual challenges. And one thing I've learned talking to fission founders in particular is that they never like to say that regulation is a problem. Like, it's shocking to me that they're like, yeah, actually regulation's great, NRC is great. So Tommy, I'm going to throw you under the bus and ask you to talk about regulation in the US and how that's holding back nuclear.
Like any other new industry that starts to bubble up in popularity, we find a way to overregulate it. In the case of nuclear, we think of fuel as one of the biggest problems that we have to solve. How are we going to get the fuel to run all these reactors? Today, most of that fuel, especially the halo fuel that we're going to need for these new advanced reactor designs, it comes out of Russia. 44% of the world's fuel for that is coming out of Russia. So what did we do? We, of course, said, well, we can't buy from Russia anymore, except for you legacy reactors that are already buying from them. Everyone else has to buy from China, which means that if you're a new entrant into the space, you're spending 3x plus on buying that same fuel because you have to buy it from China now. While the incumbents, the legacy providers, they're still getting cheap fuel from Russia. So there's no practical reason why we're making that distinction except just overregulation. We've been funding those same types of programs that are doing these new advanced reactor designs. They've been getting licenses to manufacture fuel. And then when you think about the new smaller reactors, the microreactors that need to get licensed, tested, and certified by 2026, 18 months from now, they're still having to battle with these larger incumbents to get that access to fuel. So, practically speaking, we're just not taking a very logical approach to the regulation of this fuel. For example, someone like Radiant, a much smaller reactor, needs 1/200th of the amount of fuel that some of the larger advanced reactor designs need to actually operate, run, and test. And so I think in some ways, regulation should be a sword and a shield here. We want to protect the populace, but we also have to be able to break down those barriers so that people can actually enter the market, try new things. So it's not a 6-year time cycle. So they're not building one new reactor a year. We need to iterate very quickly and get these things up and running.
Can I add one thing on that? This is the one industry, and I'd love for someone to correct me if I'm wrong, but the NRC, these companies are paying for the privilege to be regulated by the NRC versus like the FAA. Who pays for that? Like everybody in this room pays for the FAA. Everybody in this room pays for USDA. Why is it that these companies are paying for the NRC at hundreds of millions of dollars that then gets funded either by private capital or again in a different way from non-dilutive funding from the government or a variety of other sources?
So Congress just passed the ADVANCE Act. Its purpose in part is to make some of this easier. I think it's maybe supposed to lower fees a little bit. Can you talk about the ADVANCE Act and whether you think congressional support and public support is actually going to help move the needle here?
Yeah, I'm actually going to read off the acronym because I got it wrong like 3 times yesterday. It's Accelerating Deployment for Versatile Advanced Nuclear for Clean Energy Act. I think the bottom line here is it's super exciting.
There's going to be a quiz, by the way.
Yeah, exactly. It's really exciting because I think it will help. I don't think it addresses the kind of core point I just made on the fact that this regulation is still extremely expensive, but it'll certainly make it a lot easier. Some of the key areas of focus are how do we start actually exporting nuclear technology? How do we make it easier and cheaper to get advanced test reactor licenses up and running? And then what does a kind of V1 of reform of the NRC look like? And I think it's focused around some of these safety standards that are pretty archaic. I mean, obviously, we need to focus on security, but how do you do it in a way that isn't hamstringing the next generation of companies? And I think the key point here is we're in a different we're not in a nuclear arms race, but we are in a nuclear race. I mean, you look at things like, I think in the last month, Guinea and Russia signed an MOU for a floating nuclear power plant off the coast of Guinea. Like, that could be us. It should be us. Why is it not? And I think this is one step in the right direction towards how we start to decrease some of those barriers.
I love that. JC and Doug, I'm sure speaking with government customers, are they starting to view this as an arms race with China or as a geopolitical tool to use? Like, we can manufacture megawatts, use them here, ship them around the world. Is that something they're taking seriously?
Sort of, I would say, right? So when you think about nuclear, you look at economic studies, you look at markets, you really have to divide up reactors into grid scale, 1,000 megawatt reactors, what we have today. There are even larger ones than 1,000 megawatt. That's like an average. But if you've heard of SMRs, really the point of an SMR is it's about 10 times smaller, it's about 100 megawatts. The idea is instead of taking 5 or 6 years in a good scenario, you build a reactor in like 3 years, right? And so the financing charges are not as bad. You can get it turned on, making some power sooner. That's the idea there. There's a 10 megawatt size range, which is microreactors. The point of a microreactor is to exploit passive cooling. So a microreactor at about 10 megawatts, you can disconnect it from the grid, and it can actually safely cool, even with the decay heat that's generated from nuclear fuel, right? And that's the reason why an SMR is not a microreactor, and that's the distinction. It's around 10 megawatt electric that you could generate from that. What I'm working on, what Radiant is working on, is a 1 megawatt reactor, which is another order of magnitude away. So we've got 3 well, 4 orders of magnitude, 1,000, 100, 10, and 1 megawatt reactors. They're all completely different, right? And if you, there is military interest in having an outmatch capability for a near-peer adversary for a forward operating base. In the last 2 Iraqi conflicts the U.S. was in, right? We lost over 18,000 soldiers' lives. U.S. soldiers' lives lost. And they were moving convoys that were ambushed. And those convoys are moving ammo, water, and fuel. Huge amounts of fuel. Per 1 megawatt, about 4 tons per day of fuel has got to be moved. So it is really important to replace that with nuclear, make it possible to have nuclear power wherever you like to be or you need to be.
Yeah, and there was a strategic posture report that was published recently, which was bipartisan, and one of our advisors, the former Undersecretary for Nuclear Security, is one of the authors that clearly outlines that there's the first time in history where the U.S. has 2 potential nuclear peer adversaries, which has not happened before, and now there's the 2 theater scenarios. And so this really puts us in a position where we have to build now, and there's a unique time in history where the United States now is committed $2 trillion over the next 30 years to rebuild and modernize the nuclear arsenal. And this is the first time it happened since we built the arsenal. And it's a great time and window for public-private partnerships. And we were able to, last month, get the NNSA to publish that they're trying to create a NASA COTS-like program to do public-private partnership to build the next Z machine. And we've seen China invest publicly. I mean, people always question if it's true or not, but if you look at Huawei, at a bunch of other examples, better to bet that they're actually taking this seriously. But they committed $2.4 billion, was one of their most decorated scientists, to build exactly what we're doing. And I think we have a short window of opportunity to act now. I think as a private company, this gives us a good opportunity to work well in public-private partnerships so we can augment each other and work to continue to staying ahead of the race. It's a values race that I think we must continue leading.
Yeah, I mean, there's a lot of policy people, I think, who are in this room and who are going to watch this. And look, we need to wake up. We need to move faster. It's personally offensive to me that America is starting to lose on the nuclear race. My great-grandfather was a nuclear physicist on the Manhattan Project. I like to think that this is in my blood. And I'm deeply angry about this, actually, that we've fallen behind. Imagine a world in which the cheapest energy you can only get from China or Russia. Is that what we want? That's not what I want. And private companies are a huge part of that. The people on this stage are working on that, but that's also a policy thing. So everybody is involved in that fight.
Cool. All right, so how do we do this? We're talking, I think, one of the big things that I've seen in nuclear is you're moving from big bespoke construction projects where you're moving people down to a site. We just finished Vogtle. It was over budget, over cost, and now those people are sitting there trained with no nuclear reactors to build, now to making it into a manufactured product. What are some of the challenges there? What are some of the opportunities? We're at this manufacturing conference. What does it mean to manufacture megawatts?
Take a big hole in the ground, pour a bunch of concrete, work with the utility who can charge whatever price they'd like for that power when it eventually comes online, do a bunch of welding, and then weld inspections on a nuclear reactor. All things that I never want to be involved with at all, right? And at the 1 megawatt scale, instead of 1,000 megawatt, you can put a reactor just on the surface and operate it safely on a small piece of land. We can do 4 of our reactors in about 4,000 square feet, which is pretty wild. But that's one of the big problems in nuclear is that we typically think about it at this 1,000 megawatt scale. We really need to break up the markets and not just go, what are SMRs? That's a new thing, but that's about 100 megawatt. And there really are these 10 megawatt, the microreactor, and then the portable, mass producible microreactor, 1 megawatt kind of size ranges. And they're all totally different from an economic standpoint. right? So
Yeah, so like to kind of put in perspective what Doug is talking about here, like let's say you bought a Toyota Camry today, and so the CEO of Toyota called you and said, all right, we're gonna get you your Camry, we're gonna show up to your house tomorrow, and we're gonna bring the casting machines to your driveway, and we're gonna try to put the bolts together, and we'll get that thing built, right? Now it's gonna take a while because we gotta get all the machines into your driveway, and drive isn't that big. And we got to get about 600 people there to operate all those machines. Once we're done, it'll take about 2 or 3 years to get that done. We'll move all the machines again to the next driveway, and we've got a really long order book, right?
and we'll tell you what you're paying for it,
yeah, exactly, yeah. Oh, and by the way,
continuously over 60 years.
And you should continue paying us while you don't pay us at the end. Pay us starting today and pay us throughout in the entire process. And if the process takes longer, we actually make more money because the process took longer. And we're in your driveway for longer. So don't even think about going to the store for groceries tomorrow. But what we want to do instead is actually like make nuclear reactors the way more like cars are made, right? So it's not always going to be exactly one-to-one, but the way we make cars is we put all the tools and people in one place and we make them there and then we move them, right? That's how modern society creates large, complicated things. In fact, I would say more complicated things. Like if you actually look into a diesel engine, like I would argue that a diesel engine is more complicated than a nuclear reactor. It has a different safety profile, right? So we treat it differently. But the mechanical complexity of hydrocarbon drivetrains is incredible. And so we do those things in a centralized place. We make them really, really cheap, and then we move them to where they ought to be. So that's really the project of modern nuclear companies, is getting those cost curves right.
Well, and you can see in these examples, we've fallen back into our own worst habits, right? We have some programs out there, they're funding the development. Project Pele has spent $350 million with essentially nothing to show for it so far. We're behind schedule on it because there's no deliverables along that development curve, right? There's no points where we're just getting funded for development and you have to hit certain milestones to actually continue getting funded. Instead, we're using the same old type of contracting mechanisms where companies are just going to keep getting funded and they're going to get more money, and the longer it takes, the more money they're going to get. So they're just not incentivized to accelerate and move really quickly.
Yeah. JC, I know you have to leave at 11 to go just produce fusion. I really find your approach fascinating, working towards commercial fusion down the line by yourself bringing the cost of different components of a pulse power generator down that cost curve. Can you talk about how you're manufacturing fusion and working towards that goal?
Yeah, so in the approach that we've taken is essentially, we have one generator that we've built that's made of a few components like capacitors and switches, and we have to build hundreds of thousands of them. So if you break down what is the generator made out of, there's no exotic material or something extraordinarily complicated. It's just steel that's made with certain tolerances, certain sizes, capacitors and switches, and you just got to make a lot of them. And so what we've done is start building. So we actually focus from day zero on building in-house and vertically integrating a lot of the simple components. But as soon as you say, it's nuclear or defense, then the markup is 100x on basic components. And so we actually said, well, this is really dumb simple, just basic metal that you just have to make sure there's no, it's the surface finish is well done. There's no specific areas that no sharp edges, etc. And so we now have been building up, just like Lego blocks. We build components, we figure out they work, we continue mass producing them, and now we've even built technology that other companies or projects need. So that allows us to actually. For example, we built this 1 terawatt driver. We can use it for high energy lasers, high power microwaves, as well as to drive, fusion and create the conditions for fusion. And so this has helped us continue to invest in our own manufacturing capabilities while we justify the cost, so we can bring, the generator cost down, the quality higher, as well as have control over timelines. Because the other thing, even if the components are not too expensive, just because of the lead times, in the life of a startup, lead time means runway because you're burning per month. And so if something is 18 months of lead time to get it, that you should factor that in the cost of the part. And we're able to bring that from, up to 12 months to a couple of days at times.
Love it. You mentioned an important point there on iteration speed. Doug, Isaiah, JC, how important is iteration speed? And is the lack of the ability to iterate quickly, I know it's different in fusion and fission, but is that a bottleneck to the progress here?
It's the main thing. It's the main thing. I worked at SpaceX for 12 years. I built the first rocket with legs for Elon. We did that in only about a year, going from Elon saying we need it to then design, built, tested, experimental rocket permit from the FAA, flying it around in Texas and scaring cows in the nearby farm fields. They run in circles for whatever reason when you fly a rocket near them. That's their approach. Makes sense. But you know, so with a rocket with legs, that's actually a very new technology, very relevant, extremely effective at reducing the costs to access to space for everyone. But we were able to iterate. We were able to iterate really, really quickly. Part of the reason why is the experimental rocket permit is 12 pages in length, right? If you go look at that actual thing from the FAA. The NRC has produced over 440 documents called nuclear regulatory guidance documents since their inception. They've approved no new reactor designs since 1976 when they were created. And so there's a whole lot of paperwork and not a whole lot of testing. The way you know something works is by testing it, and you can test literally anything to know that it is safe. For example, they detonated the first nuclear bomb, and they looked at it. They were far enough away, they knew it was safe, and they just did the test, made sure they knew how it worked, right? So dangerous things can be tested. If they are not tested, they will not work. They will fail, and maybe in an unpredictable way, which is way less safe. So you actually need to be able to iterate. Iteration is the most important thing, and it is why we don't have mass-producible portable nuclear reactors today, because our process blocks us from being able to just access, get fuel, put it in even a subcritical configuration where we could get some test data, where we could take neutrons and digitize them to make sure that our computer codes that we're running actually match the real world. So without testing, there's a chance you diverge. Your analysis has nothing to do with the real world.
Yeah, and that's something we've been pretty focused on at Fuse. And you know, when you think about the machines that we're building and versus what exists today, like the Z machine, for example, or NIF, fire at most 200 shots per year. So if you think about their iteration speed and its different customer base and classification, so the data is literally traveling on flip-flop disks because it's the most secure way of transferring all the information. And so we're doing 10 years worth of learning in a year worth of data collection, and it's fully automated at this point and stored. And obviously we have compliance on cybersecurity, et cetera, but at least it's all in one database that's becoming the most intelligent database on nuclear and material under extreme conditions. And we've hired people from Sandia that come and they're like, wow, in a day and a half you collected more experiment than it would have taken us 2 years to do. And that's been a huge attractive for us for talent, not just from iteration speed. I mean, that's really important, but when you think about talent that's learning, they're like, wow, I can go spend 5 years at Sandia or at Los Alamos or at Livermore, and I'll get to maybe run 5 experiments. And those 5 experiments, I'll have to go fight 6 months on review board to tell them why they should give me a chance. And if my experiment doesn't work, I'm not getting second time. But that's failure is part of figuring out that something is potentially going to work, or a successful discovery of something that does not work. And I think the current infrastructure does not allow for this iteration. And that's why we're really excited to both be running experiments at 10x more frequency or rate, and second, collecting all of this data so we can have a pretty good data set to make intelligent decisions on faster.
So Morgan, I'm going to send this one over to you. How do we think about investing in nuclear? Because I think everybody in this room is probably pro-nuclear. These companies are incredibly compelling. There's a certain set of unique challenges. There's a certain set of challenges that are probably common to a lot of the things that you look at in hard tech. How do you think about underwriting a nuclear investment?
Yeah, it's a great question. And I think every investor you talk to in this space probably thinks about it a little bit differently. And then you also kind of break up, nuclear is super broad. And one of the things that I've looked to do is like go find the smartest people in this space. So I just made eyes with Will Cahill, who is the smartest person I know on SMRs in maritime, like bar none. So one of the things that I found has been super helpful is like go find the smart people and learn really deeply about the problem. Sort of breaking it down, I will completely oversimplify this on sort of the fusion world, the fission world, and let's call it radioactive isotope power systems world. And breaking it up on kind of technical risk and market risk, I would say on the fusion side, like still some technical risk. You guys just heard from JC. He knows it way better than I do. But the market's there. And then I'd say on the fission side, it's working, thank you. So the technical risk has come down a lot, but it hasn't come down a lot on the cost curve, and we still have a little bit of work to do on the market side. And then on the radioactive isotope power systems, I saw Tyler Bernstein somewhere here. He may or may not be in this room. Xenopower's a good example of this. The technical risk is really low, but the markets are super nascent, and so there's market risk there. So I would say, like, on the market front, there's a whole bunch of different ways that you can think about it. Getting to know the different folks in the space is really critical. I would also say because the technology is proliferating, there's some key questions that I would ask as an investor that I'm not sure everybody does. Like the questions like, what is your fuel source? And what does your reactor design look like? Where are you getting that fuel from? I think there's I always get this acronym wrong, BWXT. I think I got it, yeah. Like TRISO, it's a big problem. So let's have that conversation. So I think there's some, table stakes questions that we as investors can be asking to those new entrants on the scene. And I think the last thing I will add is just like every investment you make, and I know there are a lot of investors at this conference, like there's probably 60 to 80% that you can call as many people as you possibly can and like really know like backwards and forwards about a particular company. There's sort of that like 10 to 20%, it's the known unknowns. It's the part where you're like, you know what, there's risk, but let's do our best to mitigate it. And then there are those unknown unknowns that we kind of know are there, and it's really hard to figure out exactly what the contours of those unknown unknowns are going to be. One of the challenges with nuclear, and I don't think it should by any stretch hold us back, I think one of those key questions is around this kind of safety and security question. Like, we all know that it's safe, but it's sort of this fragile industry where, one mishap from a new entrant, and who knows what the response is going to end up being. And so it's there's a different set of risks that are associated with nuclear, and I think we should invest in it, but I think it's worth sort of highlighting those up front.
And Tommy, I know you've been investing in nuclear, you invested in Radiant kind of before it was cool. One, what did your LPs say? And then two, going forward, how do you think about the mix between government funding, VC funding, project financing, kind of all of that?
Yeah, when we made the first investment, I got a call from one of our LPs that thought that this was a terrible decision, and said, what happens if terrorists hijack it? And I very calmly told them that they would have abundant clean energy for 5 years. So, I mean, there's just a lot of education that still needs to be done on the fuel, on what exactly is going to, become of this market. I think I feel very similar to a lot of the people on this panel that like we should all feel a little cheated of the last 60 years of the promised future of nuclear, that it hasn't materialized. And so to Morgan's point on the risk, like it's risk capital. Like there are risks associated with this. And I think, we looked at the biggest differentiator, and obviously Doug and Bob and the team that he's built are spectacularly smart, capable, but one of the big seller for us was that their experience at SpaceX, they understood that regulation was going to be front of mind through this entire process, and that the technical development had to be done right alongside not just navigating regulation, but trying to innovate on regulation. It's really hard to innovate on systems and regulatory environments. Where we are today, and especially when we think about the fuel, if I was to look at any reactor investment today, the biggest question I would have is where are you on that regulatory timeline? Because there is no hack or amount of grit or hustle that's going to get you through the NRC regulatory pathways. So you just have to get in the trench, fill out the paperwork, the hundreds of pages of it, and you have to navigate the environment as it exists today, not as you hope it will be at some point in the future.
That's a great answer. One of the insights that when we originally spoke, I thought was really interesting that you made, Isaiah, was that utilities are actually a terrible customer for nuclear. So I'd love to hear from both you and Doug on the importance of selecting your customer when you're building, when you're building a reactor, when you're selling fuel based on a reactor.
Yeah, customers and products are actually everything in technology. Sometimes I'm an engineer, and my engineer brain, sometimes I have to switch into customer and sales mode, because it turns out that customers and products and who you are selling to and what you're selling them is actually more important than the technology behind it. Technologies shift throughout time. We don't make TVs the same way that we used to make TVs, but we're selling the same product to the same people, right? And so the technology evolves underneath. The Starship operates very, very differently than Falcon 9, but the product is the same and the customer is the same, which is Starlink to internet customers and kilograms to orbit for whoever wants to, put something up in space. And it's actually highly deterministic to your timelines and actually how you build your technology, how you're allowed to build your technology, who your customer is. And I think one of the ways that nuclear has gotten stuck is that the customer is, very, very risk-averse organizations, which are quasi-government organizations. They're not technically, but if you want to know who runs a company, figure out who backs up their debt, right? And in most cases for the utilities, that's the government. And there are a lot of organizations that function that way, and it makes them unable to purchase sophisticated technologies. Is the right way to say it, I think. There's a type of customer who wants the project to look a certain way and is going to underwrite it a certain way, and it trends towards what we've seen in nuclear, which is really, really large bespoke reactors, which are 1,000 megawatts plus. That's just what that customer wants to buy, and it's because they have certain timelines and they want it to be a certain size for their goals. It's much less of a, hey, we have this product, it's going to make some energy, we're going to slap it down and sell it to you, and much more of it's going to take 10 years and it's going to make 1,000 megawatts and it's going to be a Rolls Royce. Actually, I shouldn't use Rolls Royce in this example because now, they're making reactors too. But so utilities. There's a bunch of bad incentives in that market. They also can go bankrupt in the middle of your process, which happens a surprising amount of time. So it's a really tough sales cycle.
So talking about customers, there's a couple important points. In the last 50 years in nuclear, if we dial all the way back to the 1970s, when we had actually new designs being made, we had high temperature gas reactors, which are sort of the last category of thing that were done. Before that, in the 60s and 50s, we built literally everything you've ever heard of that you think sounds new now, thorium or molten salt or other types of reactors. We've actually not just thought about them and designed them, we built those things. They exist. Space reactors. There's a SNAP 10A reactor in orbit right now in a 400-year orbit. That's up there because we were good. We built things fast in nuclear a long while ago. The reason we don't have new reactors in all these size ranges I talked about, right, 1,000, 100, 10, and 1 megawatt, is that the customer's not there. The customer's not there is the main problem. It's not a regulator in the way. Customers might get excited about nuclear technology if they're aware of what it actually does. And in my range, a 1 megawatt completely portable unit, we can replace diesel generators out in remote regions of the world. You could take a place and go, hey, there are critical minerals here, and I want to mine them now. The DoD says I want to mine them now, right? And what we are doing makes it possible to immediately just do that. If you have So what we're on track to do right now is fuel the first reactor, new design, in 50 years, doing that just in 2026. So like less than 2 years from now, we will have that. And then mass produce these very small reactors that can be deployed in a way where you just wouldn't think about it being possible with a nuclear technology, right? But we can make, it's basically a nuclear gen set. And so I'm very careful about, building up too many customers that we can't deliver for, and just getting enough. And about a month ago, we signed a customer, Idaho Strategic Resources, which is they have a gold mine, but also they sit on top of a bunch of critical minerals, magnet metals mainly. So like neodymium, praseodymium, those metals in Idaho, and I'm really excited to work with them. It's a really small little project. Funding a reactor that's 1,000 times smaller is more than 100 times cheaper than the big one. So it's just completely different. Like these are orders of magnitude that, and so it means that there's new customer interest because what we are developing is so fundamentally different from what has been done in the past with nuclear. But I don't want to sign too many customers, right? There's a reasonable delivery cycle. And if you look at the past 50 years in nuclear, the big problem is people sign customers, they told them the power is going to be super cheap and we're going to deliver on time, and they failed to do that over and over and over in the US. Not true for the entire world.
By the way, this is pretty important to get this right and to actually build this. We're at Reindustrialize right now. This is not just about can we build reactors, which is super important, but energy cost is a huge driver to manufacturing. Energy, I think 33% of the electricity in the US goes into manufacturing. And it's one of the, levers that you have on competitiveness with another country. That's why China is building 100 reactors right now. And, also why they burn a ton of coal is because they want really, really cheap electricity to drive manufacturing processes. So if we want to reindustrialize, if we want to bring manufacturing back to America, we actually need to be able to make cheaper electricity than everybody else in the world. Now, China's answer to that is just burn a shit ton of coal, right? That's their answer to that question. And also make nuclear reactors. But one thing that I want to remind us is every time America gets into this sort of situation where we're faced with a competitor and it looks dire, we actually just innovate our way out of it, over and over and over again. That's what we do. That's what we do as Americans. We're in a pickle. We're in World War II, and we're you know what? Let's just make so many machines that we win this thing. And I think that's the approach that we should take here. But electricity, the cost of power, really is a super, super fundamental input. And actually, I think it's getting more fundamental. A lot of what you're walking around and seeing out here is about automation. And if you think about what automation really is, my good buddy Cam Schiller has a company called Rangeview, where they've reinvented investment casting, and they've been able to reshore investment casting, but not by taking the same process and figuring out how to make it slightly cheaper, by reinventing it from the ground up. And if you look at what their line looks like versus a normal investment casting line, it basically goes from people operating things to robots operating things with AI. And if you think about that, what it means is we went from people walking around paying them to lots of electricity. They actually have GPU racks sitting in their office that are running the 3D printers and the arms that are doing this. That's going to proliferate everywhere, especially in the US if we want to win, right? If we want to win, automation has to be a huge part of that play, and electricity price is directly correlated with that. I think that's actually one of the reasons that we're seeing so much nuclear development in China right now is if you start to do that math over a 10, 20, 30 year period, electricity costs and manufacturing costs start to track really closely. And so this is really, really important for us to get right. If we want to compete, we need cheaper power.
I just want to add something really quickly on Doug's point. It's a little bit of a thought experiment. The biggest drain on power in New York City, Madison Square Garden. So we're starting to think about things like, how do you ask Madison Square Garden to change its temperature from 72 to 78 when nobody's in the building? You can do that using AI that helps with grid utilization, but you could also do it with something like radiant. So there are a lot of different ways to think about this. Obviously, manufacturing is a really key piece, but we can also use it to help some of those high stress moments in our grid.
All right, so we have a last question here. Around the horn, really quick. We have less than a minute. I don't want to get yelled at. What does the energy mix in the U.S. look like in the year 2050, and what does that mean for the people in this room?
Well, I think we can easily use hydrocarbons for just flying, maybe, right, in a reasonable manner. Maybe battery electric vehicles. Maybe we can make all transport on the ground electric. That would be very cool. Take the batteries, use them for that. Don't put them on the grid as grid storage. Instead, make new nuclear designs that can throttle up and down, which of course naval reactors do very well. Our reactor also can just throttle up and down and make whatever power you like, and use as much solar, wind, and hydropower as is possible on those grids. But those things may not produce any power at night, and so you want to have. But there's less power used at night. We're sleeping, right? So maybe it looks like that generally.
I don't know exactly. I think it would be a variety of different things. Obviously, you've heard a lot today about nuclear. There's a reason why we're a nuclear navy, and the Pacific is really big, not to be pedantic about it. But how do we continue to invest in nuclear, both on the national competitiveness side, but also on the manufacturing side? I don't think fossil fuels are going anywhere anytime soon, whether we like to admit it or not, just because if we don't provide them, somebody else will. And it's tough to, we didn't talk about it a lot today, but the price of solar is tough to deny. It has come down a ton, and it's another tool in our toolkit, and we should use everything we have at our disposal.
It's definitely going to be a blended solution, but I think maybe the overarching sentiment should be that if you believe that the world is a safer, more stable place when the United States is in a position of leadership, that means technology leadership, it means energy leadership, it means leadership in defense, right? Having been a participant in a lot of government things in the past, I do know that we generally are out there trying to do what's best for not just Americans, but what's best for the rest of the world. And so I want us to be at the forefront of every aspect of energy, to include nuclear.
All right, I'm going to give you a crazy answer. I'm going to call it 99-1 nuclear to renewables. And here's why. So first of all, on jet fuel and hydrocarbons and these sorts of things, I think we actually continue as a species to use hydrocarbons for probably hundreds of years. Hydrocarbons are actually a really, really incredible way to move energy around. But I think that they're going to be generated by Valar atomics. I think that we're going to make them, and we're going to sell them all over the world. But the power source there will be nuclear. I still think there will be solar panels, and I will also say we already have a fair amount of solar capacity, and I don't think that's going away. I just think that humanity over the next 30 years is just going to use so much more energy than we're using now, which is awesome, that slowly nuclear is just going to grow into this enormous power source, and it's going to dwarf every other form of generation. You will still have solar in various places where it makes sense, solar on roofs, that sort of thing, but like the large amounts of energy that humanity is going to consume on all of our dreams of the future, going to Mars, mass-scale AI and robotics and manufacturing, nuclear is far and away going to be the powerhouse for that.
Hell yeah. All right. Thank you to our panelists. Thank you to all of you for listening. Figure out what you can do with 10 times more energy.